Okay, so let's unpack this. Imagine you're an engineer working on a really complex system.
Right, something high stakes.
Exactly. Think like the backend for Slack, Canvas, or Quip. You make a small change, a totally logical change, you commit it, and then you go check the build status.
And you wait.
You wait for an entire hour, 60 minutes.
Uh,
That hour-long feedback cycle every single time is an absolute killer. I mean, it doesn't just annoy people, it cripples the whole organization's agility.
you can't iterate. You just can't. If feedback that you broke something critical comes an hour late, you've already moved on.
So our deep dive today is all about how one team solved this exact nightmare. And what makes this story so great is that they didn't just find some new magic tool.
No, it wasn't about the tool.
It was about applying the most, classic foundational software engineering principles, but applying them to the build system itself.
That's the core insight, and it's so often missed. People see infrastructure as this separate, weird thing. But what's fascinating here is the realization that the build process, the compiling, the testing, all of it, it's just code.
It's just more code.
And if it's code, then all the performance tricks we know for applications like caching and parallelization, they apply perfectly. You can model the whole thing as a graph of dependencies.
A directed acyclic graph.
Right.
A DAG.
Exactly, a DAG.
So if the build is just one big, really expensive function, let's start with the absolute first principle of making things faster. Caching. The simple goal, do less work.
Precisely. I mean, think about any function in your code. If you call it twice with the same input, you want to store the result so you don't do the work again.
The source material uses that classic factorial n example. The number n is your cache key.
And the result is the value. Simple.
Okay, but let's pull that into the messy world of compiling code. For a build, n isn't a number. It's, what, a hash.
It's a cryptographic hash of all the inputs. All your source files, your compiler flags, everything that goes into making one artifact. The output is that built thing, maybe a JavaScript bundle or a compiled Python file.
So if the hash of the inputs is the same.
You get the output back instantly from the cache. No work done.
But, and this is a huge but, that cache is only trustworthy if the build step follows two, non-negotiable rules.
Oh, absolutely. First, it has to be hermetic.
Meaning it only uses its declared inputs. It can't be secretly reading some environment variable or a random file somewhere else on the disk.
Right. And second, it has to be idempotent. Same input, same output. Every single time. No exceptions.
And if your build step, say, sneakily embeds a timestamp or random UUID in the output,
your cache is useless. The key changes every time.
Yeah.
And getting a legacy system to be truly hermetic, that is often the hardest part of the entire journey.
I can imagine. Real-world build scripts are they're sloppy. They depend on global state machine paths.
All things that break hermeticity instantly. But once you have these clean, small, hermetic units, you can start thinking about the next level up. Cache granularity.
You want to maximize your cache hit rate.
Exactly.
So if you try to cache the result of one enormous function, like the example of images.list transforms.list.
Right.
And that list has, say, 5,000 images. You change just one of them.
And boom, the whole cache key changes. You're forced to rerun the entire thing from scratch, processing all 5,000 images again. That's a terrible hit rate. That's what we call coarse granularity.
The big insight is to break it down, decompose it. Instead of caching that huge function call, you cache the smallest possible unit of work.
Process image. Single image, single transform.
Right. So now when you add one new image, you only run the process for that one new combination. Everything else is served instantly from the cache. That small change enables massive reuse.
And once you trust your units are hermetic and small, you can tackle speed. Because even if a small unit runs once, if you have thousands of them, it's still too slow.
Which brings us to the second classic principle. Parallelization.
Sharing the load.
Yeah, this feels more familiar. We do this in our apps all the time, right? Using a thread pool executor to spread CPU-heavy tasks across all your cores.
And for builds, which are just massive computational graphs, it's even more crucial.
But just like with caching, it demands rigor. You need those same clean input-output definitions so work can be run out of order on different threads or
on entirely different machines across the network. If your steps are all tangled up or if the chunks of work are too big, you can't really parallelize effectively.
So that's the trade-off. A few huge tasks or thousands of tiny granular ones.
And the tiny ones give you maximum parallelization and the best caching. This is where the tool they chose, Bazel, finally enters the picture.
Right, so Bazel is basically an engine built from the ground up to exploit these principles.
It is. It forces you to define these small units of work, these targets, in a really formal way. You declare all the inputs, all the outputs, and the exact commands.
And if and only if you do that homework to make your steps hermetic and idempotent, Bazel gives you these three, superpowers.
That's a good way to put it.
Yeah.
It gives you automatic caching, not just for you, but for your whole team. It gives you distribution across a massive compute farm, and it guarantees it only runs the absolute minimum work required.
But here comes the reality check.
Yep, the messy part.
When the team tried to apply this beautiful theory to the actual Quip and Canvas build system, they hit a wall. Bazel was useless until they cleaned up the underlying architecture.
The first thing they found was that their dependency graph, which was supposed to be a DAG,
A nice, clean, one-way street.
was not a DAG. It had cycles. A
Okay.
depended on B, which, somewhere down the line, depended back on A.
And if you have a cycle, you can't determine the order of execution. So you can't parallelize, you can't cache. The whole system is just tied in a knot.
A total knot. Second, the build units were huge and, as you said, sloppy. Hermeticity was a huge problem because steps were just mutating the working directory, throwing files all over the place.
And the final, brutal number that proved how bad it was.
Their remote cache hit rate was 0.
0. Not just bad. 0%.
Because even if 95% of the code was unchanged, some other little input was always changing, forcing a full rebuild.
They had a great analogy for it. It was like calling a function with 100 parameters, and 2 or 3 of them were different every single time.
Yeah, and those parameters weren't even source files. They were things like environment state or, timestamps being embedded by old scripts.
So they couldn't just swap the tool. They had to perform major surgery. This gets us to phase 1. Severing the Gordian knot.
And the core problem they identified was a complete failure to separate concerns.
And it was all tangled up.
Totally. Back-end code, the build code itself, application config. You had the back-end coupled to the front-end build, Python coupled to TypeScript. It was a mess.
And they found the one single thing that was causing the most pain, the most expensive edge in the entire graph.
This is where that 35 minutes of pain came from.
The front-end build system literally had a dependency on the entire built Python backend.
Not just on some shared library or API definition, the whole compiled service was considered a transitive source for the front end.
Just think about what that means. You change one line in a Python doc string.
A comment.
A comment. The hash of the backend build artifact changes. And because that artifact was an input to the massive front-end build,
The front end's cache key changes, and it triggers a full, expensive rebuild of everything.
the cost was, on average, 35 minutes per build, over half the total time.
And the qualitative impact was that engineers just couldn't trust the system. They couldn't reason about the blast radius of a change. Every backend commit felt like a roll of the dice.
So the fix was painstaking. They had to enforce that separation. They rewrote the Python build orchestration code using Starlark.
Which is Bazel's own configuration language. It's much more constrained, so it basically forced them to separate the build logic from the application logic.
And for the Python scripts they still needed.
They stripped them down, rewrote them to rely only on the standard library. No more dependencies on internal code. It was painful, but it was the only way to get to hermeticity.
That sounds like a monumental effort, just rewriting your architecture to fit the rules of a new tool. Was that 35-minute fix worth it?
It absolutely was.
Cool.
And to make sure they didn't break things, they built a custom tool in Rust to compare the artifacts from the old system and the new one, bit for bit.
Ah, that's smart. That builds confidence.
It was critical.
Yeah.
And the result of all that cleanup was huge. They severed those key couplings.
And the build time.
It dropped to as little as 25 minutes, assuming the front end was cached. 35 minutes, just gone.
But 25 minutes is still pretty slow.
Oh, yeah. It's better, but it's not great. So that led to phase 2, the final push, which was all about that remaining front-end build time.
And this is where they found what they called a layering violation.
Hmm.
The old front-end builder was its own complex work orchestrator. It was trying to be clever and parallelize things internally.
But now it was running inside Bazel, which is the main work orchestrator. So you had two schedulers fighting for the same CPU cores and memory.
Resource contention. And on top of that, the old builder's cacheable unit was still way too big. It took in all the source files to produce all the output bundles.
Which meant changing one little CSS file for one component still meant rebuilding the entire application's front end.
So even with the back-end fix, the front-end builds were still slow and flaky.
The solution was It's kind of drastic. They just delegated everything. They started deleting code.
Deleting the old parallelization logic?
Exactly. The new front-end builder was made much, much simpler. It stopped trying to be a clever orchestrator.
It had one job.
One job. Build one specific output bundle from one small set of source files. They shattered the huge front-end build into hundreds of tiny, independent targets.
And that unlocked everything.
Instantly. Now, Bazel could see all these tiny, independent units. It could run the TypeScript compilation for one bundle at the same time as the CSS compilation for another bundle, all in parallel across the whole cluster. No more conflicts.
So by designing for composition's small, independent, hermetic units, they finally unlocked the full power of the tool.
And the final results were phenomenal. The entire effort, from start to finish, led to a build time that was up to 6 times faster than that original 60-minute nightmare.
What really stands out to me here is that these principles, separation of concerns, system thinking, composability, they aren't just for writing your app.
No, they apply to the whole system. Your build code, your release pipeline, your dev environment.
And by focusing on that fundamental design purity, they didn't just speed up the build. They made the entire application stronger.
That architectural cleanup is a huge win. It pays off everywhere, in maintainability, in debugging, in just engineering trust.
Absolutely. So here's the final thought I want to leave you with. If defining these, these clean, small, hermetic inputs led to a 6 times speed increase in this really complicated build process.
Where else?
Exactly. Where else in your daily workflow or in your organization's processes could defining granular, idempotent steps lead to these massive, unexpected efficiency gains? What hidden cycles exist in your own dependency graph that are costing you those 35 minutes of wasted time every single day? Something to look for this week.